Hey, welcome everyone. Today we have Vivek Saxena from Stony Brook or Rutgers, and he will tell us about SQFTs and topological modular forms.
Right. Thank you very much for the invitation, the opportunity to talk here. This talk will be based on a paper that I wrote last year. It's the archive number and some work in progress. And here's the plan of my talk. I'll begin with a warm-up just to introduce people to topological modular forms. I'll start with the simplest example, which is some versions of supersymmetric quantum mechanics, where you can already see some version of generalized cohomology. And then I'll move on to a brief overview of what is called topological modular forms and what's the title of this talk. And there's something called the Segal-Stolz-Teichner conjecture. So this talk will basically be about a conjecture relationship between two-dimensional supersymmetric quantum field theories with minimal supersymmetry, 0, 1, and this relationship with generalized cohomology of topological modular forms. And then I'll mention a math question in the math literature for which a physical interpretation was given in this paper. And I'll describe what homotopy of theories in the title means. It'll have something to do with two-dimensional conformal field theories that appear as worldsheet theories of non-supersymmetric heterotic strings. And I'll end with some open questions in future directions. So just to begin with, the first part of this talk will be about SQM. I'll try to be a little quick so that we can move on to the interesting things, but just want to get your attention to basically n equals 1 supersymmetric quantum mechanics. So the ingredients are a Hermitian supercharge, a Hamiltonian, which is also Hermitian, and the defining equations, Q squares equals H, and of course Q commutes with the Hamiltonian. But one key point here is that there is also a fermion number operator, which endows a Z2 grading to the Hilbert space. The Hilbert space is denoted by script H. And this anti-commutes with Q. And commutes with the Hamiltonian. This is one of the first things we study when we study supersymmetry. But there's something called the Witten index, which is defined as a trace over the Hilbert space of -1 to df with e to the minus beta h. This is called the Witten index. And because of supersymmetry, turns out that this Witten index actually only receives contributions from ground states, from states with h equals 0. And consequently, it can be computed in approximations of the theory where the theory might be more computable, and it's invariant under smooth deformations, suitably interpreted small deformations of the theory. So it's a useful object to consider. And it's assuming that the superquantum mechanics that I'm considering has a discrete spectrum. This basically just counts the difference in between number of bosons and number of fermions in the ground state. Assuming a discrete spectrum, this is a good integer valued object. But immediately, you might think this is a good invariant, but you can consider a very simple example of two systems, where system 1, system A, is a system with just a single ground state, say a bosonic ground state, and another system which consists of two extra states of positive energy. So the first system here has a Hilbert space which is one-dimensional, and second system has a three-dimensional Hilbert space. They're clearly distinct as quantum mechanical systems, but the Witten index turns out to be the same. It's just equal to 1. So the Witten index does not seem to distinguish between them. So it turns out not to be a good invariant in this sense. But if you soften your equivalence relation and say that you can always consider one system like this versus equivalent to a system like this with the addition of some sectors like this, which by the way, by themselves would break supersymmetry, then this equivalence relation is now redefined, tells you that the Witten index of the system is the same and the systems are equivalent. So it's kind of a redefinition of what it means to be equivalent. So far, you see that the Witten index turns out to be an integer valued invariant.
If we went too fast, what's the difference between A and B? The ground state structure is the same.
The ground state structure is the same, but let's say I have two additional states in an excited energy. So this is a very
Oh, you're
series
saying
system.
that's the only state?
This is the only state. So the dimension of the Hilbert space in this case is 1. And here the dimension of the Hilbert space is say 3. And this is just a very trivial system with just one boson in the ground state. So the idea is that these two systems are now considered equivalent if you allow for the addition or subtraction of such vectors. This is just a definition. So I'm just saying, if you allow for this definition, then the Witten index becomes a good invariant, quote unquote, with that equivalence condition. So that's of course well known. Now I can actually do something a little more.
So your equivalence relation allows you to move the ground states also.
Yes. Sorry, move the ground states?
Well, I mean,
Yes,
if you had 3 ground states,
Yes.
2 were bosons and 1 were fermion, and you could consider
Yes,
system
yes.
1 ground state, 1 being
Yes,
boson. They have the
that's right.
same Witten index.
Yes, that's
And you
right.
want to say kill the pair.
Kill the pair, yeah, exactly.
He's also allowing all the massive stuff to
Yes,
shift around. Even the dimension.
even the dimension.
Yeah, I understand.
I'm just saying that the Witten index would say that these systems are the same if same interpreted by that equivalence relation. For various reasons, you might not like that equivalence relation, but I'm just saying if you were to impose that equivalence relation, these two systems.
So illustration is just a statement, any theories with the same Witten index.
Yes. And in order to make that statement, I had to redefine my equation of meaning of equivalence, because by such these two systems are not the same quantum mechanically, because
But a different theory.
they're different theories, yeah. So the point is that in the rest of at a later point in the talk, there'll be invariants which sort of connect theories which are really distinct, but they're invariants in a sort of generalized sense. So of course, I can do something more. I can keep that system and I can add Majorana fermions to it. So let's say I add 2 Majorana fermions. So these are, think of them as distribution operators. If you just have 2 of them, there's a simple way to represent them on the Hilbert space. You can just write them in terms of polymatrices. Now you can check that all the equations hold. So if you have an even number of Majorana fermions, this is a well-known result. There's nothing new here, but this is just to recap, because this is the first place where something interesting happens. If you have an even number of fermions, Majorana fermions, you can represent them irreducibly on the Hilbert space like this. But what if you just have 1? So in the extreme case, instead of lambda 2, I just have 1 lambda. Then this theory, in more modern terms, is said to have a gravitational anomaly. And this turns out to be a mod 2 anomaly, because it only depends on the sign of the path integral measure of the fermions. So if you think of putting this theory on a circle of a theory with a single Majorana fermion, so let's take just a theory with 1 lambda, and you put this on a circle, what's the action? The action is something just that looks something like this. And if you compute the Hamiltonian, it turns out to be 0. So lambda is really not a function of tau. And if you put this theory on a circle, you can expand this in Fourier modes. And up to some T factors, the action looks like that. And if you do a path integral, you can see that non-zero pairs, non-zero modes have contribute an even fermion measure, path integral measure under -1 to the f, but the 0 mode is unpaired. So it's clear that this theory, this path integral measure sign choice only depends on the number of fermion 0 modes you have. And so it's a mod 2 anomaly. So it's the first example of a mod 2 anomaly, and in this, for theories with some n number of Majorana fermions, you can argue that this anomaly being a mod 2 anomaly means if the anomaly vanishes, you have the Witten index is still a good invariant, but if the anomaly So you should think of each Majorana fermion as carrying one unit of the
Why
anomaly.
is it an anomaly? Why do you call it?
It's an anomaly because, well,
I mean, other cases, some symmetry that you worry about. Here, what can you couple?
-1 to the F, for example.
Do you mean on the twisting?
Yeah, so if you have a single Majorana fermion, -1 to the F,
But there's no fermion number. Really, for odd number.
That's the anomaly.
that's the anomaly.
Okay, that's what you were calling.
Yeah, this is
Okay.
just, yeah. So now, if you have some system like this, clearly you have, so for example, if you have, to answer your question, maybe the following makes it a little clearer. So one representation of these operators is just the trivial representation where you take Q to be 0 and you take, say, lambda, the single Majorana fermion, to be sigma 1. And you can take, say, -1 to the F to be sigma 3. Because this is just a trivial system with a 0 Hamiltonian. So it gives you a representation of the algebra. It's kind of a trivial representation, but you could do something else. You could replace the 0 with some function, some number, some real number zeta times sigma 2. This system now, with this choice, with a non-zero value of zeta, this describes something in which supersymmetry is broken. So in that sense, the system with that anomaly is sort of continuously connected by one parameter deformation to something that's trivial. So I'm trying to reinterpret that equivalence relation by saying that systems with this anomaly are effectively trivial because they can be continuously deformed in a one parameter family, as an example, to systems with broken supersymmetry. So in that sense, they're trivial. So in that sense, the classification is given by an integer value of Newton index when you have an even number of such Majorana fermions. It's just trivial when you have a mod 2 anomaly of this sort. That means this this theory doesn't have a good invariant of this sort. And this is actually something, this mod 2 effect is, maybe it's going to become clear in the next part, but this mod 2 should remind you of something called complex K theory. But before I get into that, the idea is that there is some object, which is the complex K theory, and complex K theory of the point is precisely reproducing this behavior. So this set of, this is the complex K theory spectrum for a point. I'll describe all these words momentarily. But if you notice, this is identically the same thing as this. So
Wait, sorry, where did the Z come from? Why is it not Z2?
this is the Witten index. So for this is just the usual Witten index. And sorry, I should.
So -1 to the F is G2, but you could have any number of ground states.
Right. So it's still
50.
Yeah, if you have an even number of Majorana fermions, the usual Witten index is still good invariant, and it's still, for the same reasons, integer valued and well defined. So only the problem arises when you have an odd number because you can't reducibly represent them. Or well, you see, one thing I did say is if you take an even number of Majorana fermions, let's take an even number which is m equals 2n. The dimension of the Hilbert space is just going to be this, right? And if m is odd, this would suggest that you have a Hilbert space of dimension square root of 2, which makes no sense. You can't irreducibly represent it in this sense. So it would lead to some kind of an absurdity. You can recover this by looking at, say, for example, trace of -1 to the, you can compute this. So you can take trace of -1 to the F for a single Majorana fermion in the Never-Schwartz sector. In the case when it has an antiperiodic condition, you just recover square root of 2. So it's not the heuristic thing. You can actually get that. That's a known fact that in those cases when the fermion number is not a good operator, the dimension counts square root of 2 times some integers. So that's what's happening here. Okay, so all I'm saying here is that this classification of the anomaly given by some integer for even number of Majorana fermions and given by some trivial 0 for odd number is reflective of the complex K theory spectrum. And this is not just an analogy, there is a more rigorous mathematical way of seeing this, but for the moment, the physical idea, and this, as I said, this is going to be a physics talk, so I don't want to dwell too much into the math technicalities, but the idea is deformation classes of superquantum mechanics with this kind of gravitational anomaly induced by some number n of Majorana fermions, deformation classes are basically given by complex K theory. That's and this is an example of our first example of what is called a generalized cohomology theory. So let me take a few moments and describe that physically. Again, if you're mathematically inclined or already very well versed with cohomology, then this will be a very sort of pedestrian way of thinking about them. But hopefully, it's just conveys some intuitive ideas. I'm using it wrong. So all generalized cohomology theories are essentially some ways, some recipes, or some gadgets that take a topological space and map it to a sequence of abelian groups, which are generalized cohomology theories. We already know ordinary cohomology, that it turn out to be related. And underlying any generalized cohomology theory is something called a spectrum. I used that word a few moments ago. So essentially, this means you have some list of topological spaces indexed by n, and for formal reasons, n can now be negative. It's just an index, and some set of maps. And there are various definitions in the math literature about what these conditions, what these should satisfy, and they lead to various kinds of spectra. In this case, in the case of the talk today, I'm going to, so this is a topological space. And it's actually a pointed topological space, so there's a notion of a base point. And these are base point preserving maps. And I'm going to restrict myself to the situation where there is an additional condition that the maps from the space En minus 1 to the loop space of En are called weak homotopy equivalences. I'll explain that. And just to remind you, the loop space of any space is just the set of maps from a circle into that space. So the idea is that you have this a map from the n minus 1th element of this list to the loop space of the next. And the fact that this is a weak homotopy equivalence simply means that the homotopy groups of this space and this loop space agree. That's all it means. Again, we can be super technical about this, but I don't want to. And this thing is called an omega spectrum because of the omega in it. And in complex K theory, and for that matter, other variants of K theory, and also I'll argue spectra related to two-dimensional supersymmetric field theories form an omega spectrum. So this is just a definition of what it means to be an omega spectrum. But what does it do? Well, once you have this list of spaces, you can recover the cohomology groups of a space X by simply looking at the set of homotopy classes from X, your space of interest, to this space En, which is one of the lists. So if you do this, if you construct the set of homotopy classes here, you will discover the generalized cohomology. If this seems abstract, let's consider the usual cohomology that we all know and love comes from what's called the Eilenberg-MacLane spectrum. So there you take for these spaces what are called Eilenberg-MacLane spaces. So you take fix an abelian group. And the nth Eilenberg-MacLane space has the property that it only has a homotopy group of order n, and that homotopy group is A itself. And it turns out that A of an minus 1 is in fact omega of AAN. So in this case, it's actually a homotopy equivalence. And it's a bit stronger than that. If you do this and plug these spaces back here, you just get back ordinary cohomology with coefficients in A. That's what it means to think of cohomology in terms of a spectrum. So the ordinary cohomology, you can have, say, Z here, or R, or U1, or anything, any abelian group, corresponds to constructing just the homotopy classes of maps from a space of X, X of interest into the Eilenberg-MacLane spectrum. And so far, so this is an ordinary cohomology. And cohomology theories have to satisfy what are called the Eilenberg-Steenrod axioms. I won't go into those details, but the most important axiom that ordinary cohomology, can I write on this board? Or
Yeah,
I
you'll
want
be able to move it.
that should be fine. I just wanted it quick. So there's something called the dimension axiom, which simply says that the cohomology of a point is concentrated in degree 0, and it's just cohomology of a point with coefficients in Z is concentrated in degree 0, and it's just equal to the coefficients that you use. So for example, for ordinary cohomology, this seems like a standard thing that what's the simplest thing you compute is the cohomology of a point. But it turns out that generalized cohomology theories actually violate this particular assumption. And while I have, just to remind you, complex K theory, oh, it's already there. Complex K theory violates it for all even integers higher than 0. It's already true that I haven't told you what spectrum complex K theory comes from, but the recipe of what I've been saying is all generalized cohomology theories come from some spectrum, which means some set of choices of such spaces and maps satisfying some technical conditions so that there's a way to construct cohomologies from the spectrum. And it turns out complex K theory, look at the spectrum of a point, it's not concentrated at n equals 0. Overall, even integers gives you something non-trivial. So that's our first example of a generalized cohomology theory. There's, of course, more technical definitions and so on. But coming back to physics, we got this system by looking at super quantum mechanics with N-Majorana fermions. I can do two further things to it, which connect me to, just use this. I've done two complications of supersymmetric quantum mechanics. I've done two versions. One is the usual one is the one with Majorana fermions. Now I can do two additional things to it. And in the interest of time, I'll try to be a little quicker. So the one interesting thing that you could add is time reversal symmetry. So you could consider n equals 1 super quantum mechanics with time reversal symmetry. Now time reversal symmetry that I'm interested in squares to the identity, not to -1 to the f. That's an important point. Because I'm interested in time reversal symmetry that comes from 2 dimensions. And there's a reason why I should only be looking at t square equals 1. But the time reversal is implemented on the Hilbert space by an antilinear operator that squares to 1 for me. And the relation, the equations that it satisfies are t square equals 1. And also all the things that we already know from there are still true. But it commutes importantly with -1 to the f. And it also commutes to the supercharge. Now, if you can construct an irreducible representation of the operator algebra for a given theory, which realizes these operators, and they have the correct transformations on the fields, which means if you have a Majorana fermion, well, any fermion, it should act on a, the time reversal should act on it like this. That's the usual way in which time reversal acts. Of course, for a free fermion, Majorana fermionic field, I just argued that lambda is independent of t because of tau, because the Hamiltonian vanishes. So people usually write this as t lambda equals lambda t, or t lambda commutator is 0. So I can also consider a system with Majorana fermions, but at the moment, let me just look at what happens, what is the consequence of having time reversal symmetry. If you have time reversal symmetry which squares to the identity, the Hilbert space slightly changes. So when Q is square 0, the ground states look simply like this. You have your usual state, but now you can act with T and get a state with the opposite parity. So already before saying anything more, it's obvious that since all my ground states look like this, there's always a pair which is related by time reversal symmetry. The ordinary written index will vanish already. So there's no notion of an anomaly yet. I'm assuming that the system has a well-defined T operator acting on fields in that way. And if Q square is positive, now you have a Hilbert space which actually has a fourfold degeneracy. So that means not only does the ordinary written index vanish, but if states get lifted out of the ground state, they have to have this fourfold degeneracy. So what it also means, quite interestingly, is that the dimension of the ground state levels, which I write as dimension of Hilbert space graded at e equals 0, this thing is not only is it even, but it changes as a multiple of 4. So if you take half of this and reduce it mod 2, this is a good invariant for all the same reasons that the usual written index was a good invariant. This is something that's called the mod 2 written index or the mod 2 index. And it's actually in this form, it was mentioned in one of the paragraphs in Witten's 1987 paper on elliptic genera and quantum field theory. So in the old literature, it's called the mod 2 index, but when I say the mod 2 written index, that's the quantity I mean. So that's what time reversal symmetry does. And now you might wonder, what if we add these two ingredients? If we consider a system which has Majorana fermions and time reversal symmetry, and then something more interesting happens, and the system, that's my last complication of superquantum mechanics. So you have this, all the usual relationships that we had. And now, or maybe for completeness, let's consider a system in which I have n Majorana fermions. So the defining relations are the standard ones. Now, since I also have time reversal, I have this T commutes with Q, and all the lambdas commute with T. And since you have fermions, of course, you must have Clifford algebra. It turns out, in this case, the gravitational anomaly gets upgraded to a mod 8 anomaly. And that's also actually a well-known fact from supersymmetric quantum mechanics. It has interesting applications for type 1 superstring theory. There's a really nice paper by Ed Witten on this, which came out recently. I highly recommend reading it. There's a very nice discussion and an explanation for this fact that it becomes a mod 8 anomaly using just Clifford algebras, using just honest to God constructions of Dirac matrices. But it's slightly elaborate. The idea is that if you combine these two things, effectively you can cancel the time reversal anomaly by leveraging Majorana fermions. Sometimes people call these Majorana fermions spectator fermions because they're not really doing anything aside from just being a source of the anomaly. But the mod 8 effect looks like this. So if the anomaly is 0 mod 8, you have the usual Witten index. Now, if the anomaly is 1 mod 8, you have a Z2 valued object, and that's just the mod 2 index that I just explained. And it turns out to be a quick invariant even when the anomaly is mod 2 mod 8. For 3, 4, 5, 6, and 7, you have 0 here. So in the second row, I'm just writing down what the range, if you like, at this point, what the range of the good invariants would be. So when I say 0, I just mean these systems are trivial in the sense that the two indices that I introduced, the usual Witten index and the mod 2 index, they fail to say anything more about it. They're not trivial systems. They're important, and there are more subtle invariants that people have since discussed in the context of TMF. But this pattern should remind you, or if it doesn't remind you, at least you should know that this actually reproduces the KO theory spectrums. That's another version. It's called real or orthogonal K theory. It's another generalized cohomology theory. So if you compare the second line with the table, you see it's the same thing. So mathematicians Stolz and Teichner actually showed, using these arguments and slightly more technical details of spectra theory in algebraic topology, that the spectra, that the spaces of superquantum mechanics models with these symmetries form omega spectra. Remind me, we had a definition of an omega spectrum right there. And I think that's a non-trivial statement because this statement is about physical quantum field theories. Yes, they are 0 plus 1 dimensional, but you're saying that there is some topology in the space of quantum field theories that form spectra. All cohomology theories come from spectra, so saying something about the space of quantum field theories is an interesting statement, even if it's in one dimension. So that was my review of part 1. If we have this, and now we can actually move on to talk about two-dimensional supersymmetric field theories, which was the object of interest. But here we have to take a slight historical detour. But let me mention the punchline. The punchline is just like the Witten index and its versions, like the mod 2 version, were useful for classifying systems with such anomalies. There is an upgraded version that you might wonder what happens for two-dimensional theories. And that's what leads us to the subject of topological modular forms. Historically, actually, it originated with some earlier work by Edward Witten in physics, which was prompted by wanting to give a physical explanation for some mathematical properties of what happens when certain spaces have some circle action. So S1, the circle, acts on some spaces, and if these spaces satisfy some interesting topological conditions, like some characteristic classes of these spaces vanish, then there are some divisibility conditions on certain objects in math, and mathematicians tried to use what's called index theory to explain it. And this led to a subject, it's a rather esoteric subject, which is another generalized cohomology called elliptic cohomology. And in a line, let me just say that topological modular forms are some kind of an upgraded version of that. But the idea is, I've used the word genus multiple times. or invariant multiple times. And in elliptic cohomology, there's something called the genus, an elliptic genus. I'm not going to give an explanation of what elliptic cohomology is because that would take us too far afield. But in mathematics, there is a concept that if you're given a commutative ring, so this is some commutative ring. This is just going to be a very schematic explanation of what this work was connecting to and why we need to think about TMFs. So you have any commutative ring, a mathematician would define an R-valued genus as a homomorphism from some Bordism group ring. So this is a Bordism ring of manifolds with some structure V. I'll give an example in a minute. To a ring R. So there's some grading because of the ring. So the cobordism ring, well, or Bordism ring, in this context, it's a cobordism ring. Just to remind you, cobordism is another generalized cohomology theory which physicists have started using quite a lot. The idea is kind of simple. A cobordism is basically an equivalence relation if you have a manifold N1 and a manifold N2, and if there's some one higher dimensional space which smoothly interpolates between them, and there are some technical conditions on what it means to be the smoothly interpolation, then the space of such manifolds, so this is n-dimensional, and the space of such manifolds equipped with an equivalence relation, that there are two manifolds N1 and N2 are considered cobordant if there is a manifold one dimension higher which smoothly interpolates them. This forms a ring. And if these manifolds have some structure, for example, they are spin manifolds or oriented and so on, they have a tangential structure that's given by some group B or some structure, which would be like an orientation, for example, then it forms a cobordism ring, which is given by this. And you know, it's an important activity in homotopy theory and now in anomalies to compute cobordism rings for various quantum field theories of spaces with some structure. But this is what mathematicians mean by a genus, and this is said to be an important quantity because it characterizes invariants, very broadly interpreted in algebraic topology. The relation is that I've been telling you that all generalized cohomology theories come from some spectrum, and indeed you might think these cobordism rings also should come from some spectrum. So the physics understanding is that if you have a sigma model, any generic supersymmetric sigma model, you should think of it as a set of maps from some space X to some target space. Right? That's the usual thing. The string worldsheet is an example. And if your target space has structure B, like this B, then all of these sigma models essentially live in a spectrum. And that's called the Tom spectrum. So you should think of sigma model target spaces as living in a Tom spectrum. So this is a classifying space for sigma model targets, if you like. And what the genus is simply an assignment of a particular element of this Tom spectrum to some spectrum that produces a graded ring. So basically that just means if I take the homotopy of this, so this is a relation between two spectra, this is where QFTs live. And this is where sigma model target spaces live. That's the physics understanding of what it means to be a ring valued genus. So you should think of this as a classifying space for target spaces, and this as a space of QFTs. So if you have a genus, it's basically an element of some cobordism ring that's obtained from this by taking the homotopy classes of the Tom spectrum. That's what gives you cobordism ring. So remember, we had this discussion on the spectra. So from this list of spaces, I could construct cohomology and homotopy groups. In the same way, if you take the homotopy classes of the Tom spectra, you get the Bordism rings. And when people say in math, say there's something like a genus, what they really mean, if we can translate it into the language of sigma models in supersymmetry, is that this is the classifying space of targets, and it's basically the genus is an assignment that sends to a target space the corresponding sigma model. That's how you could think about it. So in elliptic cohomology, the interesting object was something called the elliptic genus. That was a particular case of this. And
There's no supersymmetry in this story.
sorry.
There's no implicit supersymmetry in the QFT.
Yes. I'm just restricting myself to SUSY QFTs.
So minimal, very minimal.
Not necessarily minimal, actually, because in Witten's work, he was talking even about type 2A and type 2B worldsheet sigma models, but I won't talk about them. But that's actually how he originally discovered the connection. So Witten, basically what Witten did was, so the math question, which then Stolz-Teichner kind of upgraded, was the following. So this is, I was just talking about what it means to define a genus. And in this context, there are two math facts which are important. One is if you have a compact differentiable manifold, well, we know that it's a spin manifold if its first two characteristic classes equal between classes vanish. This ensures orientability, this ensures spin structure. And if it's a spin manifold, then there's an additional property that holds that its first Pontryagin class is canonically divisible by 2. So it's an even class, which basically means that half of P1, which is usually written as lambda, is also an integer class. It's a well-defined, you can't do this generically, but if it's a spin manifold, it's canonically divisible by 2. And if lambda vanishes, then this is said to be a string manifold. So based on the thing that I was telling you, the corresponding Tom spectrum for string manifolds, which means sigma models with string manifolds as target spaces would be M string. I haven't really said what it is. It's some infinite dimensional abstract space. Now, string manifolds are interesting because as it turns out, the heterotic string naturally lives on them under certain conditions. I'll get to that momentarily. But essentially, the idea is that Witten's work could be described as the assignment to a string manifold of its corresponding sigma model. Let's make sure I have the notation right. So what Witten showed was that there is a well-defined map from the spectrum of string manifolds to the rational ring generated by modular forms. So that's where the connection to topological modular forms and modular forms comes in. So basically, he was looking at 0,1 sigma models. In today's talk, in terms of today's talk, he was looking at 0,1 sigma models, and he constructed their partition function and said that's in fact in the Ramon sector. And he said that's the elliptic genus up to an important p-factor. So when he wrote this down, notice that the right-hand side is not a spectrum, it's just a space of modular forms. So you take some worldsheet conformal field theory, and you construct some object, and you say it's a partition function, and mathematicians were looking for a more detailed explanation for it. Everything that we have been talking about essentially maps into having an interpretation in this kind of language where you have an omega spectrum. And when mathematicians looked for this omega spectrum, it didn't exist at the time Witten's paper came out. So he gave a construction of an object which actually had not been constructed by mathematicians. And that actually led to the development of what topological modular forms are. So topological modular forms are precisely things that would lead to this map of Witten, which is called the Witten genus map, to elevate it to the level of spectra. So you go from a well-defined Tom spectrum of string manifolds to what's called the spectrum of topological modular forms, so that everything I said before about spectra, precisely those sets of equations which are written on the left side of the board on the top, map to E of n being one of the spaces that define the TMF spectrum. I haven't really said what the spaces look like, and I won't, but at least that's the analogy here. So now let me actually move forward with this. So there was this was a parallel development in mathematics. It was this notion of topological modular forms is due to many people, but the main papers were due to Hopkins and Miller, and then they were generalized by various other people. But the idea is the question that Stolz and Teichner, now we are essentially towards the sort of end of part 2, was, is there a physics understanding of this? So the physics understanding is given by the following proposal, which is the Stolz-Teichner conjecture. And unlike the details of the supersymmetric quantum mechanics, where this relationship between quantum field theories or quantum mechanics models and spectra is sort of indisputed at this point, it's well established. This is still a conjecture. So if you take X to be some sort of topological space, think of this as a parameter space for some quantum field theory, and now concentrate on 2D 0, 1 sigma models or 2D 0, 1 SQFTs. And this space is actually naturally graded by an anomaly coefficient, which I call mu, and that anomaly coefficient is in integers. If there's time at the end, I'll explain why it's integers, but for the moment, just assume that this has a integer valued anomaly coefficient. I call this a degree, and the space of all quantum field theories,
He was the Carlson chart.
if it's a conformal field theory,
C log
It's-
minus 4.
minus twice of C minus C, right? That's right. So this is the space of 0, 1 SQFTs with this anomaly. And so the Stolz-Teichner conjecture says that we have a family, or rather, family of theories in S mu that are parameterized by X. So as I said, you should think of X as the space of couplings or deformation parameters, something like that. Quotiented by continuous SUSY preserving deformations. This quotient space of family of theories parameterized by X is basically given by the spectrum of TMF. So the right-hand side, which I haven't defined, and I probably in the interest of time, I won't define it very mathematically in literacy. It's a generalized cohomology theory which sort of upgrades elliptic cohomology, upgrades K theory, but it's the natural object which arose from the mathematicians trying to upgrade this Witten genus map to the level of spectra. So this was already constructed, and Stolz and Teichner basically gave this isomorphism. So they said, now the left-hand side, you should think of as the space of, in the spirit of this talk, you should think of it as the space of homotopy classes of maps from X to S minus mu. So this is really saying that there is an isomorphism here. So you might ask what's the motivation and so on, and we can discuss that. But if you accept this is an interesting statement because the left-hand side is completely physics, right? And it's saying that deformation classes of these theories are co-cycle representatives for a generalized cohomology. In the same way as closed forms are co-cycle representatives in DRAM cohomology. So you should think of a deformation class of a theory as a closed form in some sense in the TMFs.
So this S is some space of
Yes.
some space of theories.
Right.
Central
So
chart.
their argument is that the space of theories builds an omega spectrum. So
Okay,
it's a
yeah, that was my
well-
question. Yeah, so why would there be, why would theories of different central charge be related, the loop spaces be related to?
That's actually, I'll give an example of why they're certainly related if I didn't accept this physics argument, math argument, but it's kind of hairy. So the idea is that Graham Segal defined what he called an elliptic object. He said an elliptic object, if you use these 2D axioms for conformal field theory, an elliptic object, this is not going to satisfy you in terms of an answer to the question, but maybe it helps. An elliptic object is basically a categorical upgrade of superquantum mechanics. So it's really a two-dimensional conformal field theory. So when mathematicians say an elliptic object, you should think of it in terms of a 2D CFT. The reason why they even thought about this is because all of these cohomology theories sit in some hierarchy in what's called chromatic homotopy theory. So the lowest level is cohomology, is ordinary cohomology. At one higher level is K theory that has a height, it's called a chromatic height, it has a height 1. And at the next level are these classes of elliptic cohomologies, like ordinary elliptic cohomology, the whole math one, and the TMFs, and some variants. And it seemed like a natural thing that if there's minimal supersymmetry in superquantum mechanics, the next natural object to consider would be a supersymmetric sigma model. Why this? It's kind of related to the work of Witten because he already looked at these worldsheet models and said their partition functions have an interpretation in elliptic cohomology as elliptic genus of some cohomology. He didn't say exactly what the structure of that cohomology was, but it was sort of developing around that time. So this is a sort of loosely tied set of ideas. And I mean, as I said, it's conjectural. I cannot give you a very good understanding of why loop spaces enter here. For example, why is the one quantum field theory the loop space of another with a different central charge? I don't have that understanding myself. And I don't think to the extent I understood what Stolz and Teichner were doing, they don't give a satisfactory explanation of that either. So that's like a...
So that's not like a physics input. That's like you do this math and then it tells you that these spaces of supersymmetric quantum field.
Yeah, the proposal that there is a left-hand side physics interpretation that matches this is non-trivial. It was, if you like, it was by analogy because they proved it for quantum mechanics and K theory. We have a rigorous proof for K theory for that that those supersymmetric quantum mechanics models, which are parameterized by this. I mean, one way of thinking about it is, okay, one physics way of thinking about it, which is the spirit of the rest of my talk, at least because the rest of it is going to be purely physics, is the reason is that the only relevant quantity here is the difference of the central charges, and that's an RG invariant. So you should think of this in one of the examples that I'm actually going to try to sketch out is these deformations can be, one way of thinking about these deformations that could be triggered by a relevant operator that you could attach to a CFT that triggers an RG flow. If that relevant deformation is well defined, you can study it and it doesn't break supersymmetry, then it's a continuous SUSY preserving deformation. In that sense, it does flow to a theory which can have different central charges as long as the differences are the same. So it's the anomaly difference that in terms of thinking about CFTs, this is the relevant object, not the numbers themselves. But again, this is very highly conjectural, but essentially the idea is that.
What is the status of this conjecture if I restrict to sigma model 1-0 theories?
At least the heterotic sigma models, I would say the status is it's settled if you believe that the status of this conjecture is equivalent to saying that the heterotic string has no global anomalies.
No, but that restricts the dimension.
What
if I just say I don't care about the relation?
If you don't get
I just care about a 2D10 theory, which is defined by a sigma model as a string manifold.
I don't know if enough examples of string manifolds that we can work with sigma models have been tested. So,
well, that suggests that it's very far from settled.
Yeah, it's certainly very far from settled, and not to the extent that.
But it's settled in low dimension. Is that correct?
Yes. I mean, by settled, there is no rigorous proof that this space forms an omega spectrum.
No, but what I mean is that two different sigma models with the same C left minus C right and the same
Right.
TMF invariant can
Yes.
be explicitly deformed
That's
from each
right.
other.
That's right. So this, I should also say that this degree mu is the dimension of that string manifold for the
Yeah.
sigma model. So yeah, it's sufficiently low dimensions. It's well said.
You partly answered this before. When you say modeling by continuous SUSY preserving deformations, what's the constraint on the structure of the deformations?
No constraint, you can integrate in things.
So relevant, anything.
Yeah, exactly, like your sigma model could grow in dimension and then
Yes.
shrink in dimension.
Okay.
As long as, yeah, as long as the,
That's clear.
yeah, you have to go up and down the RG flow
Right.
for this
Right.
statement, but the up is necessary for the statement to be true.
Yeah, otherwise you couldn't interpolate between the low.
Yeah.
Yes.
I see.
Yeah. So this is related to this. This was discussed in some work by Gayoto, Johnson, Fried, and Whitland. That's what, so essentially what they were saying. So you construct, you start with the some supersymmetric sigma model, introduce a mass deformation that preserves SUSY, and you get some other sigma model, and then you do another supersymmetric deformation. Now, if you think of these as continuous deformations in the sense of being able to control them by adding something that you can then turn off, then it's in principle possible to go back. If you think of this as an RG flow, you should be able to go back in the sense that it's controllable by a parameter. That's in fact the example that I'll sketch up. But so if you assume that this conjecture is true, and by the way, this conjecture is known to be modified in some important cases already. So in theories which I won't get ahead myself, but in theories which are defined by partition functions which are actually not modular forms but mock modular forms, then there's a subtle distinction. The TMF doesn't capture it, and there's something called the Bunke-Neumann invariant, which is a more exotic torsional invariant, and that has a nice interpretation in terms of these mock modular forms. I won't get into.
There's some continuous spectrum in that setting.
I'm not so sure. You mean continuous spectrum on the CFT? No, I think not. Right, probably was a mock modularity, but probably not necessarily. But I haven't really studied those invariants very carefully. So yeah, but that's so it's already known to answer Clay's question. So in terms of being settled, there are exceptions of that sort. But as long as you look at CFTs which have like modular invariant partition functions overall, this is what you would be looking at, not some replacement of this on the right-hand side. That's what I meant. So if you take in particular, so I won't get too technical with this, but let's take X to be a point. We were looking at K-theories of a point. And in this case, this conjecture is basically the left-hand side, which was the space of homotopy classes of maps. I give an interpretation that this deformation class is a co-cycle representative. If X is a point, these are just called TMF. So the point is sort of suppressed, but it really means this. And this thing on the left-hand side, the space of maps from a point to Q, well, this is just a set of path-connected components of this. So measuring something about TMF classes is detecting something not trivial about the set of path-connected components of this minus U, or the space of quantum field theory. So in that sense, it's also sort of interesting. You might have guessed that from super quantum mechanics, but here at least there is an explicit proposal. So you can now talk about at least path-connected components in some precise sense, and if you believe the Stolz-Teichner conjecture. So let me just also comment that there is a natural ring structure on the space of theories that doesn't require TMF. Well, you can if you have two theories, P alpha and P beta, you can sum them in this space if you take their Hilbert space to be the direct sum. So that's clear. Turns out this operation corresponds to a sum operation on TMF classes. You can also multiply theories. By this I mean construct a Hilbert space which is a tensor product. So they are non-interacting. This is what people call stacking them. That corresponds to a product operation in TMF. And there's also a notion of a multiplicative unit. So this is a theory with a single gapped vacuum and no degrees of freedom. So let's call it one theory, such that one tensor T alpha is T alpha tensor one. And there's also a unit, so this is a multiplicative unit, and this is an additive unit. So the additive unit zero theory has just a trivial theory with no degrees of freedom. So these operations already turn it into some kind of a ring, but there's one other interesting operation, which is minus one times T alpha, and it's defined by taking your theory and tensoring it with what is called an half theory. So this is a 1 plus 1D CFT, which is an invertible phase. It has a one-dimensional Hilbert space, and all it does is it changes the parity of the Ramon sector ground state. So it's going to be important. So with this, with all this structure, it turns out that this space of connected components is an abelian group, which is good because this isomorphism is between a generalized cohomology theory, which you know to be an abelian group. So it wouldn't make sense if the left-hand side was not an abelian group. So it's actually an isomorphism of abelian groups. So at least from the physics side, you can say something about this space, assuming it's well defined. So can I take like maybe 10 more minutes to, or is that?
Well, sure.
Is that fine? Okay. So there are various properties of these TMFs. In the interest of time, I'll spare you with all the technical details. But I've been sort of oscillating between the math and the physics side. So let me now just say why physics is interesting. So for this problem, so there's a specific problem here that we want to construct. So assuming that isomorphism, there is a way in the math literature on TMFs to go from sigma models to TMF classes. It's complicated and not all the details are worked out. That's part of the reason for when Clay was asking why I said it's not completely settled. Physicists can concoct basically anything on the left-hand side as long as we understand them. Now, one good source of two-dimensional 0, 1 sigma models is heterotic strings. So a d-dimensional heterotic string has a worldsheet theory, which is a 0, 1 sigma model, and its central charge is basically 26 minus d. So d is actually the number of dimensions, so the number of compact dimensions is capital D, it's 10 minus d. So this is the central charge of the internal theory. So you know that you can construct a heterotic string by taking any 0, 1 worldsheet sigma model, but you can split it into a space-time part and an internal part. So for the internal part, this is the central charge. And if this happens to be, if the internal CFT, so it's definitely true that it's a CFT, but if the internal CFT has supersymmetry, then we know that the full space-time theory, final space-time theory, is going to be non-supersymmetric. And I'm going to confine my attention to d equals 1, in which case this becomes 17 3 by 2. And there are two nine-dimensional supersymmetric string theories, which are interesting in this context. One is the one based on the E8 level 1 cross E8 level 1 current algebra. And the other one is the E8 level 2 current algebra. So these define nine-dimensional non-supersymmetric string theory. And because these theories are non-supersymmetric in space-time, and they're non-supersymmetric in particular, they have a tachyon. And that tachyon is actually going to be important. So the math question, there are two math questions. The first one is, what is the TMF class of this theory? So when I write here this inside brackets, I mean a theory which is just the purely level 2 E8 current algebra. So what is the TMF?
Could I ask a question? Sorry, this is Jeff Harvey from the Sky. Why are you in 9 dimensions? Because what you said about E8 level 1 times E8 level 1 or E8 level 2 is true in 10 dimensions already. And actually 9 dimensions, you can put a Wilson line, so you could have all sorts of gauge symmetry.
Yes, so I'm going to assume that I've turned off the Wilson lines and I've just done a naive compactification of that 10-dimensional theory with which you're familiar on a circle and no Wilson lines. In fact, I'm going to turn off the Wilson lines for this discussion because the Wilson lines are crucially connected to what are called twisted equivariant TMFs, which I don't believe have been completely constructed. Does that address the question?
Yeah, thanks.
Thanks for the question. So that's one question. What is the TMF class? This should be a class. Oh, by the way, I didn't say. So for this, for a CFT, for a SCFT with this central charge, if you compute this anomaly, that will turn out to be 22 plus D. Since I said D is 1 in this talk, for us, this anomaly coefficient will be 31. So whatever this object is in TMF, it should live inside TMF 31. And another thing that I did not mention is that TMF is something called an E-infinity ring spectrum. So you have TMF subscript minus nu is TMF subscript plus nu. So I might occasionally change the sign at the expense of reducing or pulling something down. Okay, so that's one question. And there is an expectation that this should be related to an object in the mod 2 version of the elliptic genus. And it's sort of conjectured that this theory should have a 0 mod 2 elliptic genus. So the rest of this talk, I'll sketch. This will just now be strictly more of a physics argument. I'm going to essentially show you, but let me just present the punchline in the interest of time. I'm going to start from the E8 level 1 cross E8 level 1, by which, as to answer Jeff's question, I mean no Wilson line, so this is just a theory here. I'm going to argue that this is T dual to the E8 level 2 theory. So that's sort of known from, if you trust Ginspark and Waffa from the 80s, I mean, this is sort of known, this is not, but there is a way to understand this purely at the level of the 2D CFT, and it's really related to the T duality of a compact boson, which enters in a particular way. Both these theories are non-supersymmetric and have tachyons, and the idea is to add a tachyon deformation, a tachyon vertex operator deformation, which triggers an RG flow, and that tachyon vertex operator essentially can be thought of as a potential, as a superpotential for an n equals 0,1 super quantum mechanics. So it triggers an RG flow, and it triggers an RG flow, it makes certain fields massive, and if you work below that mass scale, you are just left with E8 level 2. So the idea is to T-dualize and then construct this model. And if you accept the fact that a combination of T-duality and adding relevant operators that trigger an RG flow is a continuous deformation, if you accept that the composition of these two is a well-defined continuous deformation, as a string theorist, you will say that T-duality is as good as any other operation. If you accept that, then what I'm about to sketch very briefly is going to show that these two models are continuously connected in the space of theories, in the sense that was being discussed a while ago, in the sense of going up and down the RG trajectories. So that in particular will mean that the TMF class of E8 level 2 is in fact the same as the TMF class of E8 level 1 plus E8 level 1. And it's sort of independently known from some work of Tachikawa and Yamashita that you can construct the TMF class of this by looking at a certain Adams Novikov spectral sequence. And they showed that this class is generated by a Z2 element in a group called A-31. So in particular, that is the kernel of a map from TMF to KO here. So I probably won't have time to go into this in detail. If there's additional time, then I'm happy to go in. But the idea is that you want me to sketch out the details or like some of the details, or should I just?
Maybe try to wrap up.
Okay. Maybe another 5-10 minutes is okay, strictly speaking? Or is that?
I mean, I think we can, there's a small subset of people who probably want
Okay,
to know the
so-
details.
so-
and
so let
everything
me-
else maybe
Fair
can
enough,
be.
yeah, okay, so let me just get, so I already sketched the idea. So let me just say, so if the argument looks like, sort of like this, and then I can get into the details. It turns out that I can add potential when a potential. I actually really need some of the details for this, but basically the idea is I start with a sigma model corresponding to the worldsheet CFT, and I'm able to show, so the argument proceeds in 2 steps. First, I said these theories are non-supersymmetric, so they have a space-time tachyon. The tachyon, I can count the number of tachyons by looking at the partition function of the CFT, the low-lying states. Turns out that this theory has an odd number of tachyons. Basically, this theory with the choices I made has a single tachyon, and it is parameterized by an integer m, which is odd. And provided, so I started from 10 dimensions and I put the 10-dimensional non-SUSY theories. That was Jeff's question. Put them on a circle of radius r. This R defines the compact boson in my sigma model, and provided this R satisfies a certain inequality, it's large enough, this factor is not important. For each m, provided R is larger than this number, I have a single tachyon in the theory. And when I add the tachyon vertex operator deformation and I integrate out the auxiliary fields in the heterotic sigma model, I generate a potential which looks like this. When I had the usual full S1, I had a U1 isometry around it, but this potential breaks it into a discrete isometry. In particular, it's a discrete Z mod M isometry of the U1 compact boson. And so now there are M vacua and there are an odd number of vacua. So you might think, what is this telling us about TMF? Well, that's a longer discussion, but this physics argument is kind of quick and simple. The idea is the following. I told you something about the sum of theories, and I've said that this theory has a single tachyon for each odd M, provided this is large enough. This is the condition for the tachyon vertex operator to be a relevant deformation. That's what I meant. So what I've effectively shown you is that you start with a complicated sigma model, which corresponds to the worldsheet theory of this. I'm only labeling the current algebra, but you can imagine that there are various other fields. So I'm being schematic here, I get into details, but when I add a sigma model, the tachyon vertex deformation, this triggers an RG flow. And in the RG flow, I can imagine my theory to be described by an odd number of vacua. That number is M. And at each vacuum, if I expand, I have an E8 level 2 theory. And second, I can make this a little more rigorous, but schematically, this is what it looks like. So if you assume, even though you have a finite volume, there's no spontaneous symmetry breaking. If you assume that the radius of the circle is large enough to justify this assumption, then what this is saying is that this theory sort of fractionates into M vacua, around each vacua, the theory locally looks like the pure E8 level 2, because all the other fields have been rendered massive by turning on the tachyon vertex operator deformation generated this potential. This is like a Higgs effect. It's basically giving supersymmetrically consistent masses to all the other fields. So all the fields that are left are those of the current algebra, which remain massless. You can explicitly show this. And this argument, even though I'm sketching it out schematically, is quite rigorous. There's no TMF or anything. But here's the discussion of TMF. So I said there's a notion of a sum of theories. Well, if you compute the TMF class for this theory, if you believe that TMFs are preserved in the RG flow, what this is saying is that this TMF class must be a sum of the TMF classes of the theories in the infrared, which after this setup have just been defined by a sum of M theories. So if I just add the TMF classes here, all of this is just a sum over M copies of this. So I should just get this. So physics is basically telling you that the TMF class of E8 cross E8 is just an odd number, which is the number of vacua times the TMF class of this. And since it's odd, and it's sort of known that this is a generator of a Z2 from some math reason, for math reasons, this just means that this also must be a Z2 class. So that's one conclusion for TMF. And in particular, since M can be odd, this as an equality of TMF classes must mean that the TMF classes coincide. Well, that's nice because that's exactly what we wanted to say. So this is an example where you can use some physics reasoning to connect TMF classes of apparently unrelated theories. You see, if you just started out with the sigma models, that was your question, there's no a priori reason why these two theories have something to do with each other. But the heterotic string connection is what connected them. So we were able to construct a larger model from which both of them can emerge as some 2 points in a larger moduli space. If you assume that these theories are T-dual and continuously connected to each other, I mean, when I say these theories, I mean the original parent theories, then the TMF classes turn out to be the same. So it's a somewhat non-trivial result. Of course, you might look at it hindsight and say, well, these theories were already T-dual, so what's the big deal? Well, we didn't know that the TMF classes would turn out to be actually equal. And there's one other issue. Mathematicians independently, to my knowledge, at least as of a few months ago, have not figured out how to compute the right-hand side using TMF methods independently. Even though the answer is just going to turn out to be a Z2 class, it's much more involved to take a level 2 current algebra, as I understand. This involves some equivariant constructions, and all the mathematical machinery to understand this object independently does not exist or is being developed. I mean, there may be experts who can probably do this, but at the moment, it's not known how to do this. So it's imperative, it's useful to be able to connect TMF classes that are not known using physics ideas to TMF classes that are known. But the most interesting thing for me is in this construction was an understanding that there's some preservation of RG flow condition that can be used to constrain TMF classes in this case.
There's no equivalence on the T-duality that is known, the TMF?
There is something called a Pontryagin duality, which is known for, so there is an important map. So these things fit into a spectra. Here's the spectra understanding. So I was saying a lot of things about sigma models, but here's the final crux of it. So TMF sits inside this map of spectra, basically. So this is the classifying space for manifolds with string structure. This is the classifying space of manifolds with spin structure. This is something called the Witten genus. We saw that. Now, this map is actually, this map is actually quite important physics-wise, but it's kind of opaque. So to understand it a little better, to answer your question, what you can do is you can take the homotopy of this diagram. And if you take the homotopy, you basically get a diagram which is a diagram on homotopy classes. And that's when the duality becomes a little more transparent, but it's not quite the duality we want, unfortunately. So I'll do it this way. Let's put them below. And there is a map. This is the reason why it's called modular forms. There's a map to the ring of weakly integral in holomorphic modular forms, or sort of weakly holomorphic integral modular forms. So those you know are generated by C4, C6 delta, and that's modular discriminant, but you also have to invert it because you have to allow for poles at the columns. And then there's a condition, of course, on this, and this thing maps to a power series expansion. So the reason I went through this detour, this diagram all the way in this direction with skipping over the TMF is what Witten did effectively. He took a string manifold, and for physics reasons, he realized the sigma model of it, constructed an object as a partition function, and proved modularity by writing its Q expansion for the partition function in the Ramon sector. Mathematicians sort of acted this map by introducing this new object, but there is a natural map here, which, based on what I said about superquantum mechanics, means the following. You take your string manifold, you construct a TMF class. Now, this corresponds to, assuming you believe Stolz-Teichner, corresponds to a 2D sigma model, 0, 1. That sigma model can be put on a circle, and then it becomes a superquantum mechanics, which, as I told you, the one with time reversal symmetry, is classified by KO theory, right? And now this map, which is called has a kernel and an image, and it turns out that so the kernel is called A nu, and there is a natural spectral sequence. The image is called mu. This is basically just saying that this is the kernel of this map and this is the image. And it's known that this sequence splits. So in fact, there's a simplification that any TMF class can be written as a direct sum of an object that is purely torsion and an image of this map. So you should think of this image as basically generating the KO valued invariant for the corresponding superquantum mechanics. To answer your question, the duality that mathematicians know about is in this group. That's why I kind of go to a detour to define what this group is. But this group is known to be Pontryagin dual in the sense that A nu and A minus 22 minus nu are Pontryagin duals. And the sigma models associated with them, the WZW models, have interesting properties. So there are some duality relations between the corresponding sigma models. So basically what happens is that one of them appears as the internal part of some worldsheet theory, and the other part also corresponds to a sigma model that can appear in the transverse part of the spacetime theory in a precisely suitable sense. That's the only duality that mathematicians, as far as I know, are aware of. But I don't know if they can translate this T-duality or something like this into a corresponding statement at the level of TMFs. At this point, it's too coarse for a mathematician because they will say to us basically that you took some laundry list of favorite models and then constructed dualities between them and then said the TMF classes are related. But not enough information is known to systematize duality for this group, I would say. But there is one more result. It says that this ring is 576 periodic, which means TMF 576 plus n is TMF, basically. So that can be explained because of the existence of the map here. But that's too large a number to be of some use in physics, I think. But that's what this is. So this incidentally also tells you that the theory has to have what's called a mod 2 genus, but maybe I'll end with that. Thank you.
Maybe we take questions after the.
Yeah.
She gets the minus in.
Okay. Let's take it back.
Vivek, will you lose time